Okay, well, let's try then to do it in English. So, so this series of talks are going to be about stable rationality and rationality questions. I mean in mathematics, not in sociology and other types of sciences. So I plan to have 4 parts. So today it will be essentially introduction. So introduction to classical notions of rationality, some classical results, and some recent statements. And then we'll go into discuss the specialization methods due to Claire-Voisin that allow to have some recent advances on these questions. And then I plan to discuss some computations of particular invariants that were used in this method. So invariants. And more specifically, it will be about unramified cohomology. And finally, well, I'll discuss applications. Okay, so well, now let me just recall some notions of rationality. So for this part, I'll consider K just a field. But essentially, we are going to work over the field of complex numbers in this series of talks. And X over K, say, integral variety. Then recall that we say that X is rational. So that's going to be my first notion. If X is birational to a projective space. So here, sometimes we say K rational, just to say that the rational map is defined over K. Well, a slightly different notion is being stably rational. So this means that X becomes rational once multiplied with some projective space. So if for some M, a product of X at a projective space is rational. 2 more notions. So you say that X is unirational if there is a dominant rational map from some projective space to X. Actually, you can take n equals to the dimension of X in this case over any field. And finally, let me mention a geometric notion, and let me consider here K equals to C. X is rationally connected, and I will abbreviate it as RC, so rationally connected if, well, there are many rational curves on X, so if for general pair of points, so 2 points general, there is a map from P1 to X. Normally, the image of the map is called rational curve on X that passes through these points. So 0 goes to 1 and infinity goes to X2. Okay. So this is a more geometric notion. Okay, so let me give you some examples of these notions. Well, also, I should say that, well, I put it in this way, and just from definitions, you see that we have straightforward implications from 1 to 3 and 4. Okay. And I'll tell you more about implications in the other direction. Okay. So, well, in what follows, we will consider essentially two types of varieties: hypersurfaces and some quadric bundles. So let me then fix notations. So type 1. So by xd in P and K, I will usually denote a hypersurface of degree d. Very often it's going to be smooth, but I'll make it precise when needed. And type 2, so quadric bundles. So this means I will have a map from X to P2, say over field K, and such that X, well, the map is projective, X is connected. Also, not necessarily smooth, even so is going to be the case very often. And the fibers are quadrics. Of constant dimension, say m. And so when m equals to 1, we're going to speak about fibrations in conics. Okay, so what can we say with respect to these properties? So the first type of examples, hypersurfaces of degree 2, quadrics. So d equals to 2. Then if I assume that there is a point, then it's a classical observation, then X is going to be rational. Yes?
In the example 2, you suppose that there is an embedding of X in P2 times.
Well, actually, it's going to be the case. Indeed, you will have some bundle so that you can speak about quadrics. Yeah. Okay, so in many examples of proofs of rationality, it's going to be explicit in this case. So here is my quadric, and here is a point. Okay, so point, rational point. So I'm going to consider lines through point. Okay, so I have a line through P, non-tangent to X. So this is going to give me a rational map, okay, birational map, to via second point of intersection. Okay, so second intersection point. So lines through P form a projective space, non-tangent lines an open subset, and then then you have second intersection points, and this gives you rational parametrization. Okay, so that's an example of something rational. Then unirationality, cubics in Pn. So say n. Well, I should have said smooth. Okay, X is smooth. Also, so n at least 3. X smooth, and there is a point. Then, well, there is a paper by Kohler when he treats all the cases, and he proves that X3 is unirational. Also, by some geometric constructions, but slightly more sophisticated than this one. So more generally, well, over the field of complex numbers, if I have D as at most n and xd smooth, then D is rationally connected. And more generally, actually, it holds for finer varieties. And this is a result by Kohler, Mayoka, Mori, and Campana. Okay. Well, now I gave you examples of types 1, 3, and 4, so maybe I can talk about something non-trivial about stable irrationality. So, fourth example. So, X stable irrational. So, actually, it's going to be an example of a conic bundle over P2 with affine equation of the following type. So it's a conic bundle. So here are conics. Okay, so maybe I should write A of t equals to p polynomial tx. So if you fix t and x, you have conics, where p is irreducible of degree 3 in x. So if you view it as a polynomial in x with coefficients, in the c of t, irreducible of degree 3, and a of t is going, if you assume that it's a discriminant. Then this variety is stable rational. So this is established by Beauville, Collier-Thelen, Iskovskikh, and Swinnerton d'ailleurs. Well, and there is a theory behind this property, actually. So one studies the surface over this field, defined by the same equation, okay, and the universal torsors on this surface. And actually, what one gets is that x cross P3 C is rational. Okay. So, well, we'll discuss the same types of varieties, hypersurfaces, and conic bundles later. Let me just discuss a little bit other implications of these notions. So maybe, some classification results. So let's consider this via dimension. So take K the field of complex numbers, and X smooth and projective. Let's consider the dimension of X. So if the dimension of X is 1, then all the notions are equivalent and are actually equivalent to the fact that X is a projective line. And similarly for dimension 2, all the notions are equivalent, and this follows from the classification of Castelnuovo and Rickes. So that's something that we know very well. Then, a classical question was to distinguish the classes of unirational and rational varieties. So let me discuss these cases, the examples of complex threefolds that are unirational but not rational. Okay, so X unirational but not rational, and dimension equals to 3. So, just a remark about methods. Well, in all these examples, the unirationality is proved by some explicit construction. And the classical method to establish the non-rationality, very roughly, was, start with variety X, and then produce some invariant of X that is supposed to be somehow trivial or to be some special form for rational varieties, and then establish that it's non-trivial. So that will give you, of course, a non-rationality. So I'll give you 3 examples. Okay, so x3 in P4. This is example of Clemens and Griffiths. So I mentioned that they are all unirational. And why are they non-rational? Well, because one can associate an abelian variety, the intermediate Jacobian of X, and they show that it's not a product of Jacobians of curves. And for rational variety, the Jacobian should be a product of Jacobians of curves. So this is an example of a non-rational complex threefold. Also for quartics, example of Iskovskikh and Manin. So first, unirationality. Well, it's known that some are unirational. So let me give you one example. So you have this particular equation. So 4 powers, and then okay, so exercise. Show that it's unirational, or ask your Italian friends to look at the papers of Segre, or Russian friends to look at the paper of Iskovskikh and Manin. Actually, as for cubics, for instance, there is an explicit construction, geometric construction by some projection argument, and to show that this quartic is unirational. But well, I put here some, and actually it's not known if all of them are unirational. And it would be nice to understand what is the situation here exactly. Well, about non-rationality, there is so-called rigidity method. So one shows that the group of birational automorphisms, so the automorphisms defined on some open, actually they all extend to the automorphisms of X. So there are very few of them. And for rational variety, there are many of them. And so this equality actually violates X4 to be rational. And the last example is some particular type of varieties by Artin Mumford. And so let me present it first as a double cover. So it's a double cover of P4. Ramified on a quartic. So you can view just the equation as double cover, and then you have quartic, x2, x3, or double cover of P3, I mean, sorry. So it's again threefold. And F4 of degree 4, some particular choice of F4 is needed. Then one shows that indeed there is unirationality, and to show that it's non-rational, there is a cohomological invariant. In this case, it's Brauer group that equals, in this case, again, to the torsion in the Betti cohomology, and this is non-zero. And actually, this invariance should be 0 for rational varieties, but also for stably rational. So this also shows that this example is not stably rational. Okay. Well, then, so conclusion. Coming back to the diagram at the beginning, so we know that 3 does not imply 1, right? the unirationality does not imply rationality. So also the stable rationality does not imply rationality. Actually, the example of so this example, one shows that it's not rational. Okay, so example 4 is not rational. And so I think it's the right time to mention it because the non-rationality is also established by the intermediate Jacobian criterion. Okay, so because of the Jacobian, intermediate Jacobian of X. Okay. Now, to distinguish the rational connectedness and uniruledness is still open. Well, it's supposed to be a difficult problem, and also because there are there is no methods to obstruct unirationality without obstructing rational connectedness. So it's unclear how to proceed. So for example, for quartics in P4, it's unclear what is the situation. So they are all rationally connected because, well, the degree is at most n. And some of them are unirational, but not all of them. So that's still open. Okay. Well, now let me discuss the questions of stable rationality for some types of varieties, such as hypersurfaces or conic bundles. In particular, in these classical cases, you see that in those 3 examples, the last one is not stably rational because of this invariant, and this invariant actually is a stably rational invariant. Well, those 2 invariants tell nothing about stable rationality. So hypersurfaces. So now we have a number of results for some hypersurfaces. So using this specialization method of Claire-Voisin that we're going to discuss probably tomorrow. So the first result I'd like to discuss is about quartics. So it's joint work with Alena. So if we consider quartics, and not all of them, but very general. I'll make it precise just in a couple of seconds. Very general. Then it's not stably rational. So what does very general mean? Well, when I told you general points, you didn't ask what does this mean, right? So because you know that general means for some open, right? So I remove some closed conditions. So very general means that I remove a countable number of conditions. Remove a countable number of, well, proper closed conditions on the, well, these are quartics, so they have coefficients, so I will say on coefficients of these quartics. Okay. So there are more results on hypersurfaces due to Totaro of the same spirit. Some very general ones are not going to be stably rational. So Totaro. Well, consider hypersurfaces with the following conditions. So n is at least 4, and d is at least 2, n plus 1 over 3. So these notations means the smallest integer not smaller than n plus 1 over 3. Okay, so that's an upper approximation. And so those types of hypersurfaces, very general, is not stably rational. Okay, some open questions. So, two open questions. So, coming back again to these classical results, cubics, as usual, is always a source of troubles. So, not known. So, stable rationality of cubic threefolds. Okay. And then there is a more old question by Kohler about rationality. So actually, so you see here there are those hypersurfaces of degree 4, they're not rational. So could one ever find hypersurfaces that are rational, starting from degree 4? So could one find a hypersurface in Pn for some n, okay, with n at least 4, well, okay, I will say d at least 4 because it will force n to be at least 4, such that xd is smooth, of course, and rational. Well, actually, stably rational, or okay, stably rational is also open. How could one produce stably rational? It's open. Okay. The second types of examples, quadric or more specifically conic bundles. Okay, so conic bundles or vibrations in conics. So this time I'll consider the base field, the field of complex numbers, and I will assume that X is smooth. The general fibers are going to be smooth, and then you're going to have some singular fibers. So the locus here of singular fibers is called discriminant. So definition. So D in P and P2C such that D is a locus of points with singular fibers. So this is called the discriminant. Of the conic bundle. And so in terms of this discriminant, one has several results on rationality, stable rationality, and unirationality. So first, this is due to Beauville. So D is the curve in P2, so one can consider the degree of D. So if degree of D is at least 6, then there is no rationality. So more recently, so by again this method in the second section, a result by Hassett, Crash, and Chinkel the same assumption on discriminant, at least 6. And again, X is very general. So now you know what. How should I continue? X is not stably rational. And finally, there are unirationality results by Mella. So if degree is smaller than or equal to 8, then X is unirational. Okay. Well, so these are all questions and results on particular varieties. So we're going to study methods for second and first theorems later. But let me also discuss other questions. So the questions of specialization and deformation of properties of rationality. So, who could give me an example of a family with all fibers non-rational and one fiber rational? Okay, so family with non-rational fibers and then one rational. Yes. Yeah, that's a good question, indeed. Elliptic curve, yeah. So I made a very bad picture here. I should have done something like this, right? Elliptic curves are going to specialize to nodal cubic, and this is rational. Well, with singularities, it's straightforward, but when the fibers are smooth, then it's a different question. So that's what we are going to assume. So this is number 4. Specialization and deformation. Okay, so we said the family is going to be smooth. So I mean we have some base. So I want to assume that it's projective just of finite type over C. Well, then you have the family, X over B, and I will assume that the map is smooth and projective. Okay, so the deformation property is as follows. So question, if I have one fiber that is rational, so what about others? Over complex points. So let's continue thinking about this problem. So for curves. So if I have a curve, then once we are in a smooth family, we know that the genus is constant, right? So then, because genus is constant, and I know that in one case it's 0, well, it's going to be 0 everywhere. So XB also is going to be just projective line. Well, when the dimension is 2, one also has a criterion. I guess it's Castelnuovo-Enriquez as well. Castelnuovo-Enriquez. If I consider S a smooth and projective complex surface, then S is rational if and only if I have those two cohomological invariants that vanish. Okay. And those are also going to be, so this condition to be equal to 0 is also constant in families. Okay, so then again, if I have one fiber that is rational, that any fiber is going to be rational. Well then, in dimension 3, it's still unclear. And if you ask me what I think, I tell you that not only me, but people change their minds like from one day to another one. So unclear what to say in this case. And in dimension 4, there are going to be some families with both rational and non-rational fibers. Okay, so when the dimension equals to 4, it's work in common with Van Hassett and Yurchenko. So there exists such a family, so smooth and projective, with fibers of dimension 4, such that, so we have both rational and non-rational fibers, and more precisely, the locus of rational fibers is dense with usual Euclidean topology on the base. So you have many rational fibers, but by the way, a very general one is not even stably rational. So for B, very general, XB is not stably rational. So, well, one speaks about this, well, strictly speaking, it was about deformation properties of rationality. You have one rational fiber, you ask if it could deform to something non-rational. But also one could be interested in the converse property. So the specialization, yes? Sorry? We're going to discuss it. Let me put it theorem 3 tomorrow. Specialization. So do you want to know what are those? Okay. So he's impatient. Well, I'm going to consider for any, so what are going to be fibers? So XB, I'll view them as hypersurfaces, but not hypersurfaces in Pn, but in product of projective spaces. So a hypersurface of by degree 2. Okay. So 2 on the second factor, 2 on the the first factor. And well, I'm going to consider the family of all such hypersurfaces. Okay, so X over B, and B is going to be an open in P59. So you have 59 per P59 that parameterizes coefficients for those hypersurfaces and corresponds to all smooth hypersurfaces, smooth such hypersurfaces. Okay, so then a couple of words about specialization. So let me put it in a local situation. So I have a discrete valuation ring, and I have some smooth and projective map. And I'm going to consider the special fiber that I'm going to call Y, and the generic fiber that I'm going to call X. I will assume that the residue field is, I don't know, algebraically close to just C. And the question is, what happens if xk bar is rational? So what about y? So is y rational? Okay. So the answer is yes when dimension equals to 1, right? Y projective line specializes onto projective line. 2, because y is going to be rationally connected. A specialization of rationally connected variety is rationally connected, and it's a surface, so it's rational. Dimensions 3, also true, slightly more subtle. So you use Matsusaka theorem that tells you precisely when the generic fiber is rational, then the special fiber is ruled. So ruled, that means that I have a birational map from P1 product with the surface to y. But by the way, y is rationally connected. And so the surface is rationally connected. And so it's rational. And in higher dimension is still open. Okay. So 4 open. And again, when one allows singularities, well, there are examples of something rational specializing on something non-rational. Well, in particular, the easy examples are going to be cubic surfaces, right? So cubic surface smooth is rational, but it could specialize to a cone of an elliptic curve, so it's not going to be rational. But actually, even more precisely, so with singularities, so one can assume that the singularities are terminal. So from what I understood, that these are the smallest singularities in the minimal model program. Then there are examples. Okay, rationality does not specialize. So in dimension 5 and more, there are examples of Tataro. And in dimension 4, there was a recent preprint by Perry. Okay. Okay, so that's basically the general picture. And so tomorrow we'll go into discuss methods that allows to prove these types of results, non-stable rationality for a general fiber, or these types of constructions. And we are also going to discuss invariants that go into, to obstruct the rationality. Okay. So I guess my time is over.
Do you have any questions?
Yes.
Yeah, as usual.
So which invariants, related invariants, are stable with respect to deformation and specialization? So I think you mentioned rational.
Could you speak louder? Sorry.
So for deformation deformations and specializations, which notions are invariant? So for instance, rational connectedness.
Yeah, okay. So rational connectedness is invariant. So it's a very good question.
For both?
Well, actually, when you have one fiber that is rationally connected, then, or when a smooth family, then all fibers are going to be rationally connected. Okay. Well, this is done by deformation theory. It's like some first results in this deformation theory and theory of rationally connected varieties. And otherwise, for unirationality, it's not known, because also it's unclear how to do it.
But
and so you see that for the rationality, well, that's not
what
true.
What about in uniruled or?
Unirule, well, you have this, well, I forgot about the precise statement of Matsusaka. So maybe, well, maybe we can discuss it later, but, well, you have these ruled properties that are addressed here, so, yeah, maybe we can discuss it later.
Thank Alena again.
So I'd like to encourage you to come next time, even because besides this new results, we're going to study something very basic. We're going to prove in 5 or 10 minutes that some elliptic curve is not rational. And that's a very short proof. It's not going to use anything. So that was an advertisement for tomorrow.